When we look at machine learning, there are several different problems that can be solved. So one problem that we have looked at, is binary classification. So this is basically, is this an X or not an X? So for instance, is this image a happy face or not? Is this sound saying Alexa or Hey Google or not? So those are all binary classifications. We've also got non-binary classification, so just general classification. An example of this would be, for instance, you've got a picture and you want to know whether it's a horse or a dog or a cat or a school bus or a bicycle. That'd all be a multi-class classification problem. We've also got regression. So regression is basically the idea of taking some inputs and coming up with a number, right? So here, we've got an input and we want to come out with some sort of a yes, no. Or maybe it's a probability, so some number between 0 and 1. A classification, we might want to have an input that goes into the output is one of several categories. And regression, we're just taking a number, or an input, and coming up with some numeric value. Let's talk about the history of this word regression. So back in the 1800s, Sir James Galton did a number of things. So Sir James Galton was, for instance, the first to name median. So to come up with that name. The first to come up with the idea of standard deviation. And another thing that he looked at was a problem having to do with height. So he looked at the heights of children based on their parents. So this would be, let's say, the parent height. Not sure how he did it, whether it was just the father or just the mother, or whether it was the average of the two. Not sure, but let's say it's one parent, for example. So parent height versus child height. And what he noticed is that there is, in fact, a correlation. So let's say we had the height kind of looking like this. Okay? We can, if we look at a line that best matches this, it might be, let's say, that line. So this line, by the way, is part of the linear part of the word linear regression. So if this slope of this line were 1, so if the slope equals 1, that implies that, let's say, average height parents tend to have average height children, and that tall parents tend to have tall children and short parents tend to have short children. Again, on average, any one particular child, you might have a short child born to a tall parent or a tall parent born to a short child, but this is sort of on average. So if m equals 1, this would say, let's say, that tall parents have children on average as tall. What he found is this slope was not 1. Okay? When he went to do this, he found that the slope was actually about 0.7. Okay, so what that meant is average parents tended to have average height. Average height parents tended to have average height children. Again, this is all on average. But tall parents tended to have children who were not quite as tall. Again, and this is in the aggregate on average. So tall parents have less tall children. And short parents have, again on average, less short children. Parents who are far away from the mean have children who are closer to the mean. This is what Galton termed regression, and this was Sir James Galton, and this was in the 1800s. So regression towards the mean. And it's this regression exactly because of the fact that we're starting with parents who are farther from the mean and we end up with the children who, on average, are closer to the mean. That is the best fit line here. Imagine if it went the other way. Imagine if there were like progression from the mean. That would say, on average, if you had tall parents, their children would tend to be even taller. That's not really very sustainable, right? Because then those children, their children, would tend to be even taller. So you'd have, great-grandchildren would be much farther away from the mean than their parents. So you'd end up with these, giraffe-type people, and also these, tiny short people too. So that doesn't sound reasonable. So regression towards the mean is what Galton termed this. And this is also sort of called linear regression because of the fact that we're doing this best fit line and analyzing that line. Well, this has been generalized so that we take this term regression nowadays and just say that is just any general case where we are trying to estimate a numeric value from an input. So if we're trying to estimate a child's height from the parent's height, we'll call that regression. And in that case, there is this regression towards the mean. If, on the other hand, we're trying to estimate a sales price of a house based on the square footage of the house, that's also a regression problem because we are trying to estimate the value of the house price. We can also have multiple inputs. We might want to do multiple regression, right? So we are trying to estimate what's the value of the house given the square footage, given the number of bedrooms, given the number of bathrooms, and given the, type of the roof, let's say. That's a multiple regression problem where we're trying to come up with some estimate for that. So regression is another kind of a machine learning problem that we look at. By the way, the regression towards the mean happens not only from parent to children. So if we look at parent height, child height, and we have something with a slope of about 0.7 that says that extreme parents who are far from the mean have children on average who are less far from the mean. The same exact thing is true if you look at it the other way around. So let's say you look at child heights compared to parent heights. We have about a 0.7. So that says that children who are extreme from the mean, so far away from the mean, have parents who on average are less far from the mean. Which kind of makes sense again. So if you have a tall parent, children on average are going to be less tall than that parent. If you have a tall child, parents on average will be less tall than that child. So both of them exhibit a regression towards the mean.